The sea, once it casts its spell, holds one in its net of wonder forever. Jacques Cousteau. Watch to the end. The most important structural detail appears at the very end. Cyema atrum is a member of the order Saccopharyngiformes, a lineage of deep-sea eels that abandoned conventional fish design. It inhabits depths typically between 1,000 and 3,000 meters, where sunlight does not exist and pressure exceeds 100–300 atmospheres. At first glance, Cyema atrum looks unfinished. Its body is extremely elongated, thin, and uniformly black. The pigmentation is not decorative, it is functional. Matte black coloration absorbs residual bioluminescent flashes, reducing visibility to both predators and prey. In an ecosystem governed by light signals, absorbing light is stealth. Unlike the dramatic gulper eels in its order, Cyema atrum does not possess an enormous distensible mouth. Its skull is narrow, tapered, almost delicate. The jaws are modest relative to body length. This suggests a different feeding strategy, not engulfment, but precision capture of small nekton and crustaceans drifting in the bathypelagic zone. The fins are reduced. Locomotion is slow and energy efficient. Instead of active pursuit, the eel adopts a vertical or slightly inclined posture, drifting with minimal muscular output. In deep water, energy conservation is survival mathematics. Its skeleton is lightly ossified. Reduced mineralization lowers density and supports near-neutral buoyancy. Maintaining position in the water column without constant swimming is a decisive metabolic advantage. Now consider the environment. Below 1,000 meters, temperature is stable, usually near 2–4 degrees C. Food arrives unpredictably, often as sinking organic debris or through vertical migration of mesopelagic organisms. Cyema atrum operates in this statistical landscape, waiting rather than chasing. Midway through our analysis, recall Darwin's principle. It is not the strongest of the species that survives, nor the most intelligent but the one most responsive to change. Charles Darwin. Cyema atrum represents responsiveness to pressure, darkness, and scarcity. Its extreme elongation increases surface area relative to mass, assisting buoyancy distribution. The absence of reflective scales reduces detection risk. Even its small eyes are optimized for faint light sensitivity rather than image resolution. Here is the rarely discussed insight. Cyema atrum's body proportions suggest hydrodynamic drag minimization not for speed, but for vertical stability. The elongated posterior region acts like a passive stabilizer, reducing rotational drift in weak deep-sea currents. This is not widely emphasized in popular references, yet biomechanically it explains the persistence of its ribbon-like form across evolutionary time. Reproduction follows the eel pattern of Leptocephalus larvae, transparent, ribbon-shaped juveniles that drift in upper layers before transforming and descending. This dual-phase life cycle links surface productivity to abyssal survival. Ecologically, Cyema atrum occupies a mid-trophic niche. It consumes small organisms and may itself be prey for larger deep-sea predators. Even in darkness, trophic hierarchies structure energy flow. Human interaction is virtually non-existent due to depth. Most specimens are documented via deep trawls or remotely operated vehicles. Data remain limited, which increases scientific interest. The deep ocean is Earth's largest habitat by volume. Species like Cyema atrum are not anomalies. They are representatives of a vast, understudied biosphere. Their morphology reflects constraint-driven design rather than spectacle. Black pigmentation, reduced fins, elongated body, lightweight skeleton. Every feature reduces cost and increases survival probability in an environment where wasted energy equals extinction. Cyema atrum is not dramatic, it is disciplined. It does not overpower its environment, it aligns with it. If this changed your understanding of deep-sea life, support the channel. Like this video, subscribe for precise, research-based ocean analysis, share it with someone who thinks the abyss is empty, and write in the comments which deep-sea organism we should examine next. Your engagement directly supports continued scientific content.